Okay, so we will start with Chapter 3, and this is an introduction to machine learning. So the pieces of this chapter are classification, regression, statistical learning theory for supervised learning, clustering, and recommender systems. So here we're going to go over the main problems of machine learning and the theory that goes behind them. Okay, so classification. Classification is sort of the quintessential problem of where machine learning started. So machine learning as a field grew out of artificial intelligence, which is a subfield of computer science. And the idea is that we want to teach computers by example. So if we want to teach, for instance, teach the computer to recognize images of chairs, then we have to give the computer a whole bunch of images, some of which are chairs, and we need to tell it which ones are chairs and which ones are not chairs. And it's supposed to learn to recognize chairs, even from images that it hasn't seen before, even chairs that it's never seen before. It's not like we tell the computer how to recognize a chair. We don't tell the computer a chair has 4 legs, it has a back, it has a flat part where you sit. We don't do that. We just give the computer these examples, and then it has to learn by example. Now, machine learning has close ties to statistics, and in fact, it's hard to say what's different about predictive statistics and machine learning. And these fields are very, very closely linked right now. Now, the problem I just told you about, which is identifying chairs, is a classification problem. The way that we set up the problem is that we have a training set of observations. So these are labeled images, and a test set that we use only for evaluation. Now, we're going to use the training set to learn a model of what the chair is. And the test set, they're going to be images that are not in the training set. And we're going to be able to we want to be able to make predictions on those images in the test set to determine whether or not each image is a chair. So here's the training set over on the left, and you see that so that each image is labeled as to whether or not it is a chair. And it could be that some of the labels on the training set are noisy. So for instance, there is a chair here that is clearly marked that it's not a chair. And that's okay. If one of these labels is noisy, that's fine, because as long as there isn't too many of this kind of noise, then we should still be able to learn a model of a chair. It's just that it won't be able to classify perfectly, right? And that happens. Some prediction problems are harder than other ones, but that's okay. We just do the best we can from the training data. And in terms of the size of the training data, the more the merrier, because the more examples we have of chairs and non-chairs, the better we'll be able to distinguish what is a chair from not a chair. So, we want as much data as we can to be able to train these models. Now, each observation in the data set has to be represented by a set of numbers. So this is a vector of numbers, a set of numbers, and they are called features. So I have this image here of a flower, and I zoomed in on a little piece of the image, and so that you can see the pixels in the image. And we can represent each pixel according to its red, green, blue values, like this. So maybe I put some red, green, blue values. So the image becomes this very, very large collection of numbers. So it's the red, green, blue values for every pixel in the image. So now you've represented that image as a giant collection of numbers. And in general, when doing machine learning, we need to represent each observation in the training and test sets as a vector of numbers. And the label is also represented by a number. So here the number is -1 because the image is not a chair, right? The chairs would all get labeled +1, and here this is a flower, so it gets labeled -1. Here's another example, and this is a problem that comes from the manhole example that we talked about in the last chapter, which is this problem that arises from New York City's power grid, where they want to predict which manholes are going to have a fire. So we would represent each manhole as a vector, And here are the components in the vector, right? The first component might be the number of events that the manhole had last year, like the number of smoking manholes, fires, explosions. So this particular manhole had 5 events last year. And then the second feature would be the number of serious events that happened last year. So this particular manhole had 3 serious events, so there you'd get the number 3. And then you'd have the number of electrical cables. So this manhole has 120 cables in it, so it's a fairly dense manhole. Number of cables that were installed before 1930 would be another feature. Whether, then the next feature is whether the cover is vented. So if the cover is vented, you could call this variable 1, and if it's not vented, you could call it 0. So vented covers means that there's holes in the covers that allow the gases to escape, which might mitigate the seriousness of an event that could potentially happen. So you want to have these sort of dummy variables that represent yes, no, the observation has this property. Whether a manhole was inspected, and then you could have many, many other variables here. These are variables that we actually used in our prediction problem. So we had over 100 of these features that we designed. Now, in general, the first step of doing this, right, is to figure out how to represent your data as a vector. You can make this vector very large. You can include lots of factors if you want. Computationally, things are easier if you use a smaller number of features, but then you risk leaving out information. So there's kind of a trade-off right there that you're going to have to worry about, and we'll talk more about that later. But in any case, you can't do machine learning if you don't have your data represented this way. So that's the first step. Represent your data as numbers, as a set of features. Now you'd think that manholes with more cables, with more recent serious events, etc., you'd think that those kind of manholes would be more prone to explosions and fires in the future. But what combination of these features is going to give the best predictor? How do you combine them together? How do you combine these features together to form a predictive model? And you could add them all up, but that might not be the best thing to do. You could give them all weights and add them up, but how do you know the weights? And that's what machine learning does for you. It tells you what combination of these features to use to get the best predictors. Okay, so for the manhole problem, we want to use data from the past to help us predict the future. So for instance, the feature data might be from 2014 and before that, and the label would be 1 if the manhole had a fire or an explosion in 2015. So that might be our training set. And then for the test set, the testing feature data might be from 2015 and before, and then you try to predict what happens in 2016. Okay, so just to be formal about it, each observation is represented by a set of numbers which are called features. So here, for instance, the manhole is represented by that set of features, and then you have another manhole represented by its set of features, and so on and so forth. So these are the features. They're called X. And then the labels over on the right, they're either +1 or -1, depending on whether the manhole had an event in a particular year. And those are the labels. They're called Y. Now, the features are also called predictors, covariates, explanatory variables, or independent variables. So you can use whatever terminology you like, but I'm generally going to use the terminology of calling them features. So even more formally, we are given a training set, which are feature labeled pairs, xi, yi, and there are n of them. And we want to create a new classification model, F, that can predict the label y for a new x. So that's the formal definition of classification, where the y's are plus or minus 1. Now let's take a simple version of the manhole example, where we only have 2 features. And those features happen to be the year that the oldest cable was installed and the number of events the manhole had last year. So you want to think that sort of the older the cables and the more events the manhole had last year, the more potentially vulnerable it is. Okay, so each observation can be represented here by a point in 2 dimensions on a 2-dimensional graph, which means I can plot the whole data set. So here's my plot, and I have a manhole that this gives us, so for each manhole, the x1, the first x, is the oldest cable, which is on the x-axis, and then on the vertical axis you have the number of events that happened last year. Okay, so each manhole is a point somewhere in this space, and if the manhole had an explosion, I would label it with a plus, and if it didn't have an explosion, I would label it with a minus. And now what my goal is to construct a function which is positive where the manholes had explosions, and it's negative where they didn't have explosions. And where the function f of x equals 0 is called the decision boundary. So we're trying to create this function which eats the number of events last year and the oldest cable and spits out whether or not it thinks the manhole will have a fire and explosion next year. Okay, so then we can create, this is not just for manholes. We can also do this for the image recognition problem that we talked about before, where we want to recognize chairs. So all of the images of chairs would be represented on one side of the decision boundary, and all the images of non-chairs would be on the other side. And hopefully, if we've done this properly, then our decision boundary will give us a good way to determine which new images that we haven't seen before are going to be chairs and which ones are not going to be chairs. So if you give me a new x, something not in my training set, so some point somewhere in this space that's not in my training set, then I want to be able to use the sign of that function f to figure out what the class is for that new x. Okay, so the machine learning algorithm will create the function for you. It might be very complicated, but the function itself might be very complicated. You feed the machine learning algorithm all this data, it produces this function f for you. It might give you a complicated function, but the way you use that function is not complicated. The way you use it is very simple. The predicted value of y for a new x is simply the sign of the function f of x that comes out of the machine learning algorithm. Now, yes or no questions, that's the most basic type of machine learning problem. That's a classification problem. And there are many, many classification problems out there, including the following: automatic handwriting recognition. So when you write a check and that check goes into an ATM, there is a machine learning algorithm that's operating on that image of that check and classifies each digit that you write, or each letter that you write, as to what letter it actually is. Speech recognition. Speech recognition relies on machine learning. You talk into the microphone of the computer, it takes that sound signal, and then it has to classify what are the words that you're saying. Biometrics, like you put your fingerprint somewhere, and it's got to classify is this fingerprint yours or not. Document classification. For instance, we want to know whether this particular document is relevant to the database query you did. Is this particular document relevant to the Google search that you did? Spam detection. Is this email spam or not spam? That's a classic classification problem where machine learning has been used for many years. Predicting credit default risk. Right? The banks want to know who they're going to give loans to, so they have to be very careful in how they determine who they're going to give these loans to. So if I give you this loan, what's your chance of defaulting? And for that, people are using machine learning. Detecting credit card fraud. Is this particular transaction fraudulent or not fraudulent? Predicting customer churn. Companies want to know like phone companies. They want to know whether a customer is likely to move to a different company, and then maybe they could try to offer that customer some more incentives to keep them around. Predicting medical outcomes like strokes or side effects from drugs. There are many, many different classification problems that arise in the healthcare domain. Okay, so the next part of this chapter is on regression. Now, regression, as I mentioned, is for predicting real-valued outcomes. It's not a binary decision. Here it's something real-valued. So for instance, how many customers are going to arrive at our website next week? Or how many TVs will we sell next year? Or someone's income. Can we predict someone's income from their click-through information? So the fact is that, how many, if you're asking how many, it's a regression problem. Now for regression, again, each observation is represented by a set of numbers. So here we have our features, which again they're called X, and we have our labels, which are called Y. But the labels, instead of being plus or minus 1 valued, they are now real valued. Okay, so let me just start with a very simple regression problem where we have a single feature. So this is one feature called X, and I'm trying to predict our label called Y from X. And the reason I want to do it in one dimension is because then I can plot X and Y on the same on a plot. So I'm going to plot X on this axis and Y on this axis. So here, I'm going to try and solve this problem. I'm going to try to predict someone's income from the number of clicks on the Business Week website that they make. Okay, so they could go from 0 clicks to 2,000 clicks. And I'm going to assume that if they click on Business Week websites a whole lot, then maybe they make more money. Okay? So let me formally define the problem of regression before I get too far into the example. So formally, given my training set of XY pairs, and I have n of them, I want to create a regression model F that can predict the label Y for a new X. Okay, so here my function F is a function of the number of Business Week clicks. So I'm trying to predict a function that will tell me, given the number of Business Week clicks, what is the income. Now, you might notice that this particular function that I have here is not so good. Why not? It's because it totally overfits the data. Look, it's like memorizing the points here. This isn't really capturing the general trend. The general trend is sort of maybe curved a little bit at the beginning and then a little more straight upward. I mean, this model won't really be great for predicting the incomes of new people that come in. So here's the opposite extreme. Oh, yeah, this is the opposite extreme. This function is very, very simple. It just says, all right, I'm going to just create a line here. So it's 5,000 times the number of Business Week clicks plus 100,000. Okay, so this has the opposite problem. This is perhaps potentially underfitted. This is a very simple function. Maybe not so great. What we'd really like is something that fits it, but also generalizes to new data. So that this function would sort of be something that is just right. And we're going to talk a lot more about this in the next part of the chapter where we talk about supervised learning. But that's in general what you want to do. You want to hit on the function that's not underfitted, not overfitted, something that's just right. So we can use more than one feature, and we could create a function that eats, like, the number of visits to upscale furniture websites, the number of Business Week clicks, the number of distinct people that they email per day, and so on and so forth. And then you can create a more complicated function that hopefully predicts well. Okay, so something like, they get 3 points for each time they visit an upscale furniture website, 10 points for the number of Business Week clicks, and so on. So this is just a weighted combination of the features, but this function F could be quite a lot more complicated. It could involve some very nonlinear transformations of the variables, and it can be a very, very complicated function. But that might be what we need in order to predict well. We might need to combine the features in a complicated way. Okay, so classification and regression are supervised learning problems. What that means is that the training data has ground truth labels to learn from. Okay, it has the either classification labels, yes or no, or it has the regression labels, which are real valued. Now, there are many, many other supervised problems, and I just want to point out that supervised learning algorithms are much easier to evaluate than unsupervised problems, simply because you have ground truth that you're working with. So in the next part of the chapter, I'm going to discuss overfitting and underfitting and statistical learning theory for supervised learning. So right now we're going to talk about statistical learning theory for supervised learning. Now, learning theory stems from the principle of Occam's razor in some sense. So Occam's razor, this is sort of a generic principle which says, in some sense, the best models are simple models that fit the data well. So it's not just having an explanation for the data, it's actually also that the explanation is simple. That's the important point here. So William of Ockham is this English friar. He's a philosopher, and he basically said that among all hypotheses that predict equally well, we should choose the one with the fewest assumptions. And somehow that translated into statistical learning theory as, okay, let's try to fit the data well, but we want to also have the simplest model. And there's a way we formalize this in statistical learning theory. Okay, so I want to give you really just the sort of essence of it without getting too much into the complexity of learning theory, which is actually a very deep mathematical theory. So here we have this very overfitted model, which is not good. So this describes the data, certainly, but is it the simplest model that describes the data well? No. Because when you have new data that you haven't seen before, this model may not generalize to those new data. Okay, so this is not the right model. So the quintessential figure that describes statistical learning theory is the one that I have shown you here. So what I've done is on the horizontal axis, I've listed the models in order of complexity. I have simple models on this side, and I have more complex models on this side. Now, if I choose an overly complex model like the one on the previous slide, my training error will go down to 0. That means I can fit the data perfectly. Okay, but my test error will be very high because on these test points that were not in the training set, I will perform very, very badly. Okay, so that's a very overfitted model. Now, if you go simpler and simpler and simpler and go down to the underfitted side, then you have a very, very simple model and it just doesn't fit the data well. So if it doesn't fit the data well, the training data well, how's it going to fit the test data well? What you want is something that's in between. You want a model that fits the data well, but also fits the training data well, but also generalizes well to the test data. Okay, so this is the sort of basic understanding of statistical learning theory. If you understand this figure, that's the essence of it. Okay, so we need a balance between accuracy and simplicity. So the most common machine learning methods, they choose that function f to minimize training error. So they try to make sure the model does really well in the training set, but they also want to keep the model simple. So you want to minimize some balance between training error and the complexity of the model. And this aims to thwart what's called the curse of dimensionality. If you have a lot of features, then it's going to be very, very hard to fit that model without an absolute ton of data. But if you can keep your model simple somehow, then hopefully you can still perform well even if you have quite a lot of features and not an absurd amount of data. And that's the whole goal of, in some sense, the whole goal of machine learning. I mean, you know, Occam, he probably didn't know optimization, right? But this would have suited him just fine, I'm guessing. That's my guess, if he were alive now. So I think what I want to do now in the next part of this chapter is switch gears completely and talk about clustering. Now, in clustering, we don't have this idea of underfitting versus overfitting in the sense that it's not supervised. So it's really going to be a very different topic. All right, so we will talk about clustering now. Clustering is an unsupervised type of an unsupervised learning problem. Unsupervised means that the training data has no ground truth labels to learn from. In the supervised setting, we knew for each image whether it was a chair or not a chair, and we were trying to figure out whether a new image was a chair or not. But that's not the setting of unsupervised learning, where you just don't have any labels. So in clustering, what we're trying to do is group these observations into similar sets of similar observations. Okay, now because it's unsupervised, these are much harder to evaluate. These problems are much harder to evaluate because you don't have ground truth to tell you that you've done the clustering properly. So, but clustering is a key unsupervised problem, and people do it all the time because ground truth is not often known. So for instance, if you have to cluster products automatically, that's not something you necessarily have ground truth for as to what the best clustering is, or if you have to cluster customers or some other thing like that. But this is a very important problem that people solve all the time. Okay, so what I'll talk about next, I'll switch gears again, talk about matrix factorization, and that will wrap up this chapter. This part of Chapter 3 is about recommender systems, and I'm just going to introduce the basic problem of recommender systems. So this problem, the kind of quintessential example for it is the Netflix contest. So Netflix, the company, they offered $1 million to any team that could design a better recommender system for movies to their customers. So this is the data that Netflix had available. This is some of the data they had available, kind of the most important piece, which is the ratings that each customer had for each movie. So for instance, like we know that Carmen watched movies A and C and D, and she gave movie A 5 and C a 4 and D a 1. And then the idea is that we could try to use the crowd's votes, right? Try to use the other customers to figure out what to recommend for her next of the movies that she has not watched. So that's the kind of problem that we're going to solve in the recommender systems part of the course. And this problem, by the way, is supervised, right? You can actually leave part of your data out and evaluate the quality of your algorithm on it. So it is therefore a supervised problem. Okay, so that is the end of this chapter, and I just want to go over what we're going to do next. So we will talk about how to formulate and solve machine learning problems, and we'll talk about how to evaluate machine learning problems, because as I mentioned, the evaluation is actually critical. If you don't know how to evaluate the quality of the method, there's no point in doing it at all. So we'll go over how to do the evaluation. Okay, thank you.